It reaches 3,000 degrees Celsius, hot enough to vaporize bone. Hot enough that the electrodes themselves glow like the gates of hell. When it fires, it doesn't just melt steel, it turns air into plasma. A controlled bolt of lightning, caged inside a refractory line vessel, fed by enough electricity to power a small city. They call it the electric arc furnace. It's the reason every crushed car, every demolished bridge, every scrap of yesterday's steel becomes tomorrow's skyscraper. It revolutionized an entire industry. It also killed the men who ran it. Before we're done, you'll understand why this beast changed everything and what it cost. We're going to find out how they took the impossible, an electric arc hot enough to melt iron, and turned it into the backbone of modern civilization. And we're going to see what happens when 3,000 degrees meets water in the wrong place at the wrong time. When lightning became the furnace London, 1808, Humphrey Davy stood before the Royal Institution with 2,000 battery cells stacked behind him. Nobody had ever seen what he was about to do. He brought 2 carbon rods close together. The voltage jumped the gap. The arc cast a light brighter than the sun, generated heat that could melt metal, and kept burning as long as the current flowed. The room went silent. Davy had just discovered the electric arc. But here's what nobody understood yet. He'd also discovered the future of steelmaking. It would just take another 92 years to figure that out, because in 1808 there was no way to use Davy's discovery. You needed thousands of batteries to create the arc. You needed a power source that didn't exist. Commercial power plants wouldn't arrive until 1882. The dynamo, the machine that would actually generate electricity at scale, wasn't invented until 1866. Davy had found the key, but there was no lock to fit it into. The world was not ready. The infrastructure did not exist. The vision was decades ahead of reality. The arc sat there for decades. A scientific party trick, brilliant light, tremendous heat, absolutely useless. Engineers looked at it and saw potential. But potential doesn't melt iron. You need power. Industrial quantities of power. The kind that didn't exist anywhere on Earth in 1808. For 70 years, the electric arc remained a scientific curiosity. Then, in 1878, Wilhelm Siemens, already famous for inventing the regenerative furnace, saw something nobody else did. He saw the arc and thought, steel. He built 2 experimental furnaces, one with electrodes top and bottom, one with horizontal opposing electrodes. In 1879, at the Siemens Brothers Charlton Works in London, he demonstrated his invention to members of the Iron and Steel Institute. He melted 2 kilograms of steel scrap in about 20 minutes. The arc worked, but the power still wasn't there, not enough electricity, not cheap enough, not reliable enough. The demonstration proved the concept, but proving a concept and changing an industry are different things. Siemens needed more. The whole world needed more. They needed someone who understood that the arc wasn't just a heat source. It was a revolution waiting to happen. The real breakthrough came in 1900 in the French Alps, a place called La Praz in Savoy. A man named Paul Héroux built the first commercially successful electric arc furnace for steel. Héroux wasn't like other inventors. He was high-strung, unruly, occasionally hard and insolent, according to those who knew him. He loved billiards, women, and travel. His discoveries didn't come from long nights in a laboratory. They came out of the blue, sometimes during a lively game of billiards. Genius hiding in a restless body. He'd already co-invented the process for smelting aluminum in 1886, made aluminum cheap enough for everyone, and now he was after steel. At La Praz, he had something Siemens didn't. 3,000 horsepower of hydroelectric energy pouring down from the mountains, 13,000 by 1895. Enough power to feed the beast, water falling from alpine heights, turned into electricity, focused into an arc that could melt iron. The physics finally matched the ambition. His furnace worked. It melted steel from scrap. It could produce specialty grades, tool steels, spring steels, alloys that the old blast furnaces struggled with. By 1907, the first Eru furnace arrived in America. Sanderson Brothers Steel Company, Syracuse, New York. That furnace, old number 1, sits today in Pittsburgh, Pennsylvania, at Station Square. A monument to the machine that changed steel forever. But here's what they were really up against. The old way, the way steel had been made since the Industrial Revolution, was the blast furnace. 30-story monsters that required iron ore mined from the earth, coal baked into coke, limestone flux, and uninterrupted operation for years at a time. You couldn't start one. You couldn't stop one. They ran hot for decades. To build one cost $1,000 per ton of annual installed capacity. You needed a harbor to ship in the raw materials. You needed an army of workers. You needed capital that only giants like Bethlehem Steel and U.S. Steel could afford. The blast furnace was king, and it was a tyrant. The tyranny wasn't just economic, it was logistical, geographic, political. If you wanted to make steel the old way, you built near a harbor. You built near coal mines. You built where the raw materials were, not where the customers were. The furnace dictated everything. It ran continuously because shutting it down meant weeks of lost production and expensive restart procedures. It was inflexible, immovable, unstoppable. A monument to industrial centralization. Eru's arc furnace offered something different. It ran on electricity and scrap. It could start and stop whenever you wanted. It didn't need iron ore. It didn't need coke ovens. It could be built for $140 to $200 per ton of capacity, 5 times cheaper. And it could sit anywhere you had power and scrap metal. No harbor required. Regional production, flexible production. Steel made near the markets that needed it from the waste those markets produced. When they first fired up those early furnaces, people called the product electric steel. A specialty item, expensive, niche. The big steelmakers looked at it and shrugged. Let Eru have his toys. We've got the real steel. We've got the blast furnaces. They had no idea what was coming, but it wouldn't happen fast. For decades, electric arc furnaces stayed small. Specialty products, tool steel, spring steel, calcium carbide for carbide lamps. The first furnaces held 5 to 25 tons. Tiny by industrial standards. During World War II, arc furnaces proved their worth making alloy steels for weapons. Specialty grades the blast furnaces couldn't match. But even then, they were the exception. The blast furnace still ruled, still poured out the bulk tonnage that built cities and bridges and ships. The question hanging over the arc furnace, could it scale? Until 1969. The plasma cage. You want to understand the arc furnace, you start with the electrodes, 3 of them in a typical AC furnace. Massive graphite rods, round in cross-section, made of segments threaded together like pieces of a giant screw. Each segment might be a meter long, half a meter in diameter, pure graphite. Carbon compressed and baked until it can conduct 44,000 amperes without disintegrating. As the bottom segments burn away in the heat, and they do, constantly, you thread new segments on top. The electrodes hang from the roof of the furnace, lowered and raised by hydraulic cylinders or electric winches. They're the conductors, the lightning rods, the weapon. Below them sits the vessel, a steel shell lined with refractory brick, heat-resistant material that can survive sustained contact with molten steel. Magnesia carbon brick, high alumina brick, materials engineered to withstand thermal shock, chemical attack, erosion from molten metal. In larger furnaces, the shell is water-cooled. Copper panels and water jackets keep the outer structure from melting. The hearth, the bottom of the furnace, is shaped like half an egg in modern designs, lined with more refractory. The whole thing sits on a tilting platform so you can pour the molten steel into a ladle when it's ready. The engineering is elegant. The reality is brutal. Here's how you light it. First, you charge the furnace. The retractable roof swings open. An overhead crane carries a massive bucket. A basket with clamshell doors for a bottom, filled with scrap steel. Could be shredded cars. Could be old appliances. Could be heavy beams and slabs from demolished buildings. 80 tons of it in a modern mid-sized furnace. The equivalent of 40 automobiles, enough scrap to fill a large room. The crane positions the basket over the open vessel. The clamshell opens, the scrap falls. A cloud of dust rises, loose steel particles, rust, paint, whatever was clinging to the scrap. If the furnace is already hot from a previous heat, that dust can ignite into a fireball. Flame shooting 20 feet in the air. The operators know to stand back. They have seen it happen before. The flash, the heat wave, the roof swings back into place, sealed. Now comes the bore-in period. The electrodes lower toward the scrap. Slow, controlled. The positioning system monitors the resistance, the current, the voltage. When they get close enough that the gap is small but the voltage is massive, the electricity jumps. It arcs, and when it does, it ionizes the air in the gap, turning it into plasma. The arc forms 3,000 degrees Celsius, 5,400 Fahrenheit. The temperature at the arc itself can hit 4,700 to 7,700 degrees Celsius under perfect conditions. Hotter than anything you'll find outside a star. The light is blinding. Even through protective glass, even through welding shields, it is like staring at the sun. Even through protective glass, it's like staring at the sun. The operators don't look directly at it. They watch gauges, meters, indicators. They listen to the furnace. The sound changes as the arc stabilizes or doesn't. The current doesn't just jump between the electrodes and hang there. It passes through the scrap. The arc heats the metal directly, both by radiation and by current flowing through the charge itself. The scrap begins to melt. As it melts, it collapses inward. Pieces shift, fall. The arc length changes. The electrodes have to adjust constantly. The regulating system tries to maintain constant current and power, but during bore-in, it's chaos. The arc extinguishes, reforms. The scrap shifts under the electrodes. The current swings wildly, 44,000 amperes or more, fluctuating, creating voltage flicker that ripples through the electrical grid for miles around. Lights dim in nearby neighborhoods. Sensitive equipment trips offline. This is the most unstable phase, the most violent, the most dangerous. But if you survive it, the scrap melts. Once you've got a liquid pool of molten steel at the bottom of the furnace, sitting there at 1,600 to 1,800 degrees Celsius, the real work begins. Oxygen lances inject pure oxygen into the bath. The oxygen reacts with carbon in the steel, burning it off. Decarburization. This reaction releases energy. Chemical energy adding to the electrical energy. Heat piling on heat. It also produces carbon monoxide gas, which bubbles up through the molten steel, foaming the slag on top. That foam is critical. It covers the arc, reducing heat loss. It shields the refractory lining from thermal damage. It keeps the furnace from tearing itself apart. You add fluxes, lime, fluorspar, other chemicals to bind impurities and adjust the steel's chemistry. You control the temperature by adjusting the power, the oxygen flow. You watch the bath, sample the chemistry, check the carbon content, the phosphorus, the sulfur, and when the chemistry is right and the temperature is right, you tap the furnace. The whole vessel tilts on its platform. Molten steel pours through the tap hole into a preheated ladle, glowing orange-white. Liquid metal at 3,000 degrees. 80 tons of it in a mid-sized modern furnace. From cold scrap to liquid steel in about 50 minutes. That's the machine. That's how it works. But here's the part they don't tell you in the engineering manuals. It works in conditions that shouldn't be survivable. The graphite electrodes, they're burning, always. You're replacing segments constantly. If the electrode oxidizes too much, it gets thin and snaps, a hard break. If the electrode shell cracks or the welds fail, molten graphite paste flows out, a soft break, liquid carbon running down the outside of the electrode like lava. If the copper tiles that grip the electrode arc across the shell, you've got an electrical fire inside a 3,000-degree furnace, Every one of these failures can happen while the furnace is running, while 80 tons of molten steel sit below. The refractory lining, it's under thermal attack every second. 3,000 degrees on one side. Thermal cycling, hot to cool to hot, dozens of times a day. It cracks. It erodes. The molten steel finds the cracks and works its way through. Eventually, molten steel leaks through. When that happens, the steel burns through the outer shell, the structural supports, the tie rods, the springs, everything. Large leaks mean catastrophic damage, and if you're standing nearby when it happens, you're in the path of molten metal moving at 1,600 degrees Celsius. The water cooling system? Copper panels, water jackets, pipes running through structures exposed to radiant heat from a 3,000-degree arc. The thermal stress is constant. The copper expands and contracts. The welds fatigue. The panels crack. Water leaks. And when water meets molten steel, you get an explosion. That's not a design flaw. That's physics. Water at room temperature contacts steel at 3,000 degrees. Instant conversion to steam. 1 liter of water becomes 1,700 liters of steam in a fraction of a second. Expansion. Overpressure. The furnace erupts. Molten metal ejected. Debris flying. The roof blows off or the shell ruptures. Anyone nearby doesn't have time to run. They knew this from the beginning. They built the furnaces anyway, because the alternative was the old way, the blast furnace, the inflexible tyrant. The arc furnace was dangerous, yes, but it was the only way forward, feeding the lightning. The men who ran these furnaces weren't stupid. They were skilled. They were brave. And they worked in conditions that would break most people. Start with the heat. You're standing near a vessel that's radiating energy from a 3,000-degree plasma arc. Even with protective gear, even with distance, the heat is constant, oppressive. You sweat through your clothes in minutes. Your skin burns if you get too close. The air shimmers. The furnace operators, the ones at the controls during melting, are closest to it. They manage the electrodes, watch the arc, control the power, decide when to inject oxygen, when to add flux, when to tap. Every decision matters. Every minute of delay costs money. The pressure to keep moving is immense, but rush, and you risk disaster. Then there's the noise. The arc discharge is loud, tremendously loud. Not just loud, it's a physical assault. The plasma crackling, the electrodes humming, the current surging, the scrap collapsing. You can't hear warnings. You can't hear your crew. You communicate with hand signals. You watch. You learn to read the furnace by sight and feel because your ears are useless. Some operators go deaf over the years. Gradual hearing loss from decades of standing next to controlled lightning. The dust. When you charge scrap, it raises clouds of metallic particles. Fine particulate matter, PM 2.5, that contains iron, aluminum, zinc, manganese, lead, chromium, nickel, cadmium, mercury, arsenic. Polycyclic aromatic hydrocarbons, dioxins. You breathe it. You try not to, but you do. It settles in your lungs. Studies on electric arc furnace workers show increased rates of diabetes, cardiovascular disease, and lung cancer. The dust alone is killing you slowly, year by year, shift by shift. You know it. Everyone knows it. You work anyway because the job pays, because your family needs it. You know it. Everyone knows it. You work anyway. But it's the sudden dangers that keep you awake. The electrodes have to be monitored constantly. If one breaks, hard or soft, you've got to replace it or repair it while the furnace is hot. Sometimes you can pull the broken section out and thread a new one on. Sometimes the break is deep inside the furnace, and you're fighting to extract a piece of electrode that's still glowing red while molten steel sits below. The graphite paste has to be maintained at the right level. Too low, and the electrode doesn't bake properly. The copper tiles have to stay tight. If they loosen, you get arcing. Arcing means fire. Electrical fire. Fire inside a furnace means you're fighting flames you can't put out with water while managing molten steel below. The refractory lining has to be inspected between heats, repaired when possible, replaced when necessary, often while the furnace is still warm. You can't wait for it to cool completely because time is money. You're working in a space that was recently holding 3,000-degree steel. The residual heat alone can injure you. Burns through gloves, through boots. Thermal shock, when you apply water to something that's been superheated, can crack components, cause leaks, create the conditions for explosion later. You patch what you can. You pray the rest holds. And then there's the tap hole. The tap hole is how you pour the steel out. It's a hole in the side of the furnace, angled down toward the ladle position. When it's time to tap, you open it, drill it out or burn it through, and the molten steel flows into the ladle. Gravity does the work. Simple. Except when it isn't. Sometimes the tap hole blocks. The steel freezes in the opening because the temperature dropped, or slag clogs it, or debris gets stuck, or the previous tap didn't clean out properly, and you've got solidified steel in the channel. When that happens, you've got 130 tons of molten steel sitting in the furnace, with no way to get it out. The temperature's rising because the arc's still on. The chemistry's going bad because the oxygen's still reacting. The furnace is a ticking bomb. Clearing a blocked tap hole means getting close to that hole, close to the furnace, and physically breaking through the blockage. You use oxygen lances, drills, bars, whatever works. You're working with tools near molten metal at 3,000 degrees. If the blockage breaks suddenly and steel pours out while you're there, you're dead, burns over your entire body. If the furnace erupts while you're clearing it, if the water leak you don't know about finally reaches the molten steel, you're dead. Explosion, debris, molten metal spraying. The tapping operators and their helpers do this job. Every tap, every time. They know the risks. They have calculated the odds. They have accepted the danger as part of the job. They've seen near misses, close calls. They've heard the stories from other plants. But the steel has to flow. The production schedule has to be met. Someone has to do it. They know the risks. They have calculated the odds. They have accepted the danger as part of the job. They've seen near misses. They've heard the stories. But someone has to clear the tap hole. Someone has to keep the steel flowing. For months, you keep the beast running. You manage the electrode breaks. You patch the refractory. You clear the tap hole. You watch the water cooling system for leaks. Listen for the hiss of steam. Look for wet spots on the floor. Check the pressure gauges. You know the risks. You know the procedures. You know that one mistake, one overlooked warning, one ignored leak, and everything goes wrong. And then it does. When the steel screamed Louisville, Kentucky, March 21st, 2011. Carbide Industries plant. The furnace wasn't making steel, it was making calcium carbide for welding and chemical production, but the principle was the same. Electric arc, molten material, 3,800 degrees Fahrenheit in the vessel. 4 workers were investigating a water leak. They'd noticed it earlier. Steam, water pooling. The leak was getting worse. Standard procedure said, shut off the water, evacuate the area, shut down the furnace. They didn't evacuate. Maybe they thought they could fix it. Maybe they were under pressure to keep production running. The pump kept running. 200 gallons of water per minute pouring into the furnace for at least 7 minutes. When water hits molten material at 3,800 degrees, it doesn't just boil. It flash converts to steam. Instant expansion. 1 gallon becomes 1,700 gallons of steam in milliseconds. The pressure inside the furnace spikes. Overpressure event. The furnace couldn't contain it. The furnace exploded. It ejected solid debris, powdered debris, flammable gases, molten calcium carbide at 3,800 degrees. 2 workers died. 2 others were injured. The Chemical Safety Board investigated. They dug into the plant's history. They found a pattern. Small water leaks over the years. Minor explosive incidents. Pops, bangs, small ruptures. Each one a warning. Each one ignored. Deferred maintenance. Repairs postponed because shutting down meant lost production. The company knew the furnace was failing. They kept running it anyway. The CSB report was damning. 2 men dead because maintenance got deferred, because warnings got ignored, but it was too late for the 2 men who died. Coatesville, Pennsylvania, May 2007. ISG Plate, LLC, 165-ton electric arc furnace, 3 steel workers working adjacent to the furnace. Inside, a stray electrical arc, maybe from a loose connection, maybe from a crack in the refractory, created a water leak on one of the water-cooled shell panels. The leak was significant, internal, pressurized water accumulating inside the furnace cavity. The operators didn't know. The leak was hidden. They kept running. Standard operations: melt the scrap, refine the chemistry, bring it to temperature. When the molten steel reached pouring temperature, about 3,000 degrees Fahrenheit, they moved to tap. But the tap hole was blocked. Standard problem. Happens all the time. They worked to clear it. Oxygen lance, drilling, standard procedures. When they succeeded, when the blockage broke and the tap hole opened, the furnace erupted, violently. John Miller, 34 years old, father of 3, standing at the controls. The explosion killed him instantly. 2 others were injured by the blast. Hot steam, flying debris, molten steel droplets. OSHA investigated. Their findings were damning. No guardrail on the platform at the time of the incident. No written procedures for clearing a blocked tap hole. No written procedures for what to do when there was significant water in the furnace. Basic safety measures missing. Management failures. The workers were doing their jobs with inadequate protection and no clear protocols. 6 years later, May 2013, same facility, Coatesville. Water leaked into the arc furnace again. Another explosion. 3 workers injured, 2 critically. Burns, respiratory damage. Despite the safety measures supposedly implemented after the first accident, despite the investigation, despite the dead, the pattern repeated. Knoxville, Tennessee, May 2014. More than 1,000 gallons of water poured into a 2,900-degree furnace through a leak. The water contacted the molten steel. Hydrogen explosion. The rapid decomposition of water into hydrogen and oxygen, then ignition. The furnace ejected fragments of molten metal and debris. 1 steel worker killed, 5 injured. The workplace had procedures. Evacuate when there's a leak, shut off the water, sound the alarm. But on that day, something broke down. The workers stayed, maybe trying to fix it, maybe not understanding the danger. The pump ran. 200 gallons per minute for at least 7 minutes, and then the explosion. 1 dead, 5 injured, families destroyed. Pueblo, Colorado, June 2021. Ivraz Rocky Mountain, steel plant, Saturday evening shift. 130 tons of steel in the furnace at maximum temperature. Workers on the floor, standard operations. Then the furnace exploded. No warning, just eruption. 8 steel workers injured, 3 critically. 2 transported for respiratory injuries, lungs damaged by superheated steam and gases. 1 to a burn unit in Denver for burns on the hands and face. 7 of them had to walk themselves out of the plant because emergency response was overwhelmed. 1 drove himself to the emergency room later because he didn't realize how bad his injuries were until the adrenaline wore off. 1 worker who knew the facility called it a way scary place. The plant had 14 OSHA inspections over the previous decade. They'd found violations, safety issues. In 2012, a machine operator was killed, run over by an industrial truck. The penalty? $8,000. $8,000 for a dead worker. That's what a life was worth in the regulatory calculation. These aren't isolated incidents. They're a pattern. The pattern is always the same. Water leaks from the cooling system. Thermal stress cracks the panels. The welds fail under constant heating and cooling. The copper jackets rupture. Maintenance gets deferred because shutting down the furnace costs money. Small leaks turn into big leaks. Workers notice. They report it. Management says keep running. We'll fix it next shutdown, next month, next quarter. And then one day, the water hits the molten steel and the furnace explodes. The Chemical Safety Board called it a deadly but preventable problem. Preventable, that's the key word. Not inevitable, not acceptable, preventable. OSHA issued safety bulletins, industry groups acknowledged the risk, papers were written, conferences held. But as of the investigations in the 2000s and early 2020s, there was no comprehensive industry standard specifically targeting electric arc furnace explosions, no mechanical integrity program requirement, like there is for chemical plants, no unified safety protocol that every plant had to follow, recommendations, guidelines, best practices, but no standard with teeth. The men who died weren't stupid, they weren't reckless, they were doing their jobs, they were following orders, they were trying to keep the furnace running, because that's what paid their families, that's what kept the plant open, that's what kept steel flowing to construction sites and manufacturers and all the industries that depend on it. And the furnace killed them. That's the cost. That's what the revolution demanded. Every bridge remembers Charlotte, North Carolina, 1969. A company called Nuclear Corporation of America, later renamed Nucor, was facing bankruptcy. They made steel joists and deck for construction, but they were dependent on a single supplier who kept raising prices, profit margins vanishing, the company dying. The president, a man named Ken Iverson, made a decision that the big steelmakers thought was insane. He decided to build his own steel mill, not a blast furnace, an electric arc furnace, a mini-mill. At that time, the vast majority of American steel came from blast furnaces. Giants like Bethlehem Steel and U.S. Steel controlled the market. They had the capital, they had the infrastructure, they had the harbors and the ore and the coke ovens and the political connections. They had everything. Iverson had none of that. What he had was scrap metal and cheap electricity, and an electric arc furnace that could melt that scrap into steel for a fraction of the cost. The big steelmakers laughed. A mini-mill? Making steel from scrap? That's for specialty products. Tool steel, spring steel. You can't compete with us in bulk production. Structural steel, rebar, the bread and butter of the industry. You don't have the scale, you don't have the tonnage, you'll fail. In 1969, Nucor opened its first mini-mill in Darlington, South Carolina. The furnace worked. It melted scrap. It produced steel, structural steel, rebar. The products, the giants said, couldn't be made economically in a mini-mill, and it did it so cheaply that Nucor could undercut the giants on price. The revolution had begun, and the giants did not see it coming until it was too late. Other companies followed. Mini-mills spread across the eastern United States, then across the country, then across the world. Post-war Europe, devastated and capital poor, built mini-mills because they were fast and cheap. You could build one in a year, get it producing steel in 18 months. No decade-long construction, no billion-dollar investment. Developing nations built them for the same reason: regional steel production, local recycling, economic development. By 1975, electric arc furnaces accounted for 20% of U.S. steel production. By 1996, 39%. By the 2000s, approaching 50%. The giants were losing market share, losing money, losing relevance. Today, Nucor is the largest steel producer in the United States. They operate 24 scrap-based electric arc furnaces with the capacity to produce almost 29 million tons of steel annually. They're also North America's largest recycler. In 2014 alone, they used over 19 million tons of scrap steel, every crushed car, every demolished building, every refrigerator and washing machine, back into the furnace, back into the cycle. That's the legacy. Every crushed car, every demolished building, every scrap of steel from yesterday becomes the raw material for tomorrow. The blast furnace digs iron from the earth, burns coal, emits CO2 as a chemical byproduct of turning ore into metal. 2 tons of carbon dioxide for every ton of steel. The arc furnace takes what already exists and melts it with electricity. 75% less carbon dioxide per ton of steel. The difference is staggering. Infinite cycles. Circular economy? It's not just a furnace. It's proof that industry can be sustainable. The old steelmakers didn't see it coming. They thought the mini-mills would stay small. Niche products, structural steel, rebar, nothing important. But Nucor didn't stop. In 1989, they opened a flat-rolled mill in Crawfordsville, Indiana, the first in the world to produce quality sheet steel using thin slab casting and an electric arc furnace. Sheet steel. The product that built cars and appliances and everything the integrated mills thought they owned. The product that required perfect metallurgy and tight tolerances. Nucor proved it could be done with scrap and electricity. The giants started falling. Bethlehem Steel declared bankruptcy in 2001. U.S. Steel survived, but barely. Smaller, weaker, a shadow of what they'd been. The industry had changed. The arc furnace won. Today, if you drive across a bridge in America, there's a good chance the steel came from an electric arc furnace. If you live in a building with a steel frame, same thing. The rebar in the concrete, the beams holding up the roof. Yesterday's scrap, tomorrow's infrastructure. The first Héroux furnace, the one Paul built in 1900 in La Praz, France, sits in a museum now. The Museo della Scienza e della Tecnica in Milan, Italy. A monument to the beginning. You can see it. Touch the refractory. Look at the electrodes. Imagine it running. The first American furnace, old number 1 from Sanderson Brothers in Syracuse, sits at Station Square in Pittsburgh, Pennsylvania. Designated a historical landmark by the American Society for Materials. A plaque explains what it was, what it did, what it started, but the technology didn't stop. It evolved. First-generation furnaces in the early 1900s held 5 to 25 tons. Regular power, simple controls. By the 1930s, 100 tons. By the 1950s, 200. By the 1970s, 400 tons. Ultra-high power, water-cooled walls, oxygen injection, computer controls, sophisticated metallurgy. Today, the largest furnace in the world operates in Tokyo, Japan. A 420-ton DC arc furnace fed by 8 transformers, delivering 256 megavolt amperes of total power. Enough electricity to light a city of 50,000 people. Enough power to run thousands of homes, all of it focused into a single arc. All of it concentrated into one point where plasma meets steel. All of it concentrated into one point of 3,000-degree plasma. And they're still improving. Hydrogen-based direct reduction to replace natural gas in the pre-melting process. Renewable electricity sources making the process even greener. Advanced automation reducing human exposure to danger. AI controls predicting failures before they happen. The arc furnace isn't going away. It's the future. Green steel, sustainable steel, circular steel. But the danger hasn't gone away either. The men who died in Louisville and Coatesville and Knoxville and Pueblo didn't die because the technology failed. They died because the same physics that makes the furnace work, 3,000 degrees, molten steel, water cooling under thermal stress, creates conditions that can kill you if you're not careful. And sometimes, even if you are, you can engineer better controls, better monitoring, better maintenance protocols, but you can't change the physics. Water plus molten steel equals explosion. That's thermodynamics. That's reality. The Chemical Safety Board recommended mechanical integrity programs, regular inspections, preventive maintenance, written procedures. OSHA issued bulletins. Industry groups acknowledged the problem, but there's still no unified standard, still no requirement with enforcement power. The explosions still happen. The water still leaks. The furnaces still erupt. Because you can't change the physics, you can only respect it. Paul Héroux died in 1914, just before the First World War. He was 51. Kidney trouble. He'd made a fortune from aluminum and steel. Married twice. Left 5 children. His furnaces were spreading across Europe and America. He never saw what they would become. Never saw Nucor. never saw the mini-mill revolution, never saw steel become circular. Ken Iverson died in 2002. He'd turned a failing company into an American industrial giant. He wrote a book, Plain Talk, Lessons from a Business Maverick, that became a case study at Harvard Business School. He proved that the mini-mill could beat the giants. He changed an industry. He showed that you could recycle forever. The workers who died in the explosions, most of them don't have memorials, no monuments, no plaques. They have OSHA reports, Chemical Safety Board investigations, a few lines in a news article. Families who lost fathers, husbands, brothers, that's the price that got paid. That's the cost of the revolution. We look at a bridge and see steel. But it's not just steel. It's the arc that Davy discovered in 1808. It's the vision that Siemens couldn't quite realize. It's the men who figured out how to cage lightning in a refractory-lined vessel and use it to melt iron. It's Davy discovering the arc. It's Siemens proving the concept. It's Eru building the first commercial furnace. It's Iverson betting the company on a mini-mill. It's the workers who fed the beast every day, knowing it could kill them. It's the dead of Louisville and Coatesville and Knoxville and Pueblo and all the others whose names we don't know. The arc furnace changed everything. It made steel circular. It made it sustainable. It proved that yesterday's waste could be tomorrow's infrastructure, infinite cycles, infinite possibility, but it demanded payment, in blood, in burns, in explosions, in men who went to work and didn't come home. They don't make them like that anymore, not the machines, and not the men.